Hello, this is my English speaking practice. I haven't recovered from my sickness. I haven't fully recovered from my sickness, and I still have throat ache. So I will do this as long as I can speak. I can speak as long as I can speak comfortably. Okay, let's go to the problem. Next number of provinces. There are n cities. Some of them are connected while some are not. If city A is connected directly with city B and city B is connected directly with city C, then city A is connected indirectly with city C. A province is a group of directly or indirectly connected cities and no other cities outside of the group. You are given N1N matrix is connected where is connected ij equal 1 if the I city and the j city are directly connected, and is connected ij equal to 0 otherwise. Return the total number of provinces. Okay. Example 1. 1 and 2 are connected and 3 is not connected, so the province is 1 and 2. And this map is represented by like this. So this is about 1, city 1. It connected to 1 is connected to 1. Okay, but the problem doesn't mention about it. Okay, the I and I is always 1 because it's identical. So 1 1. City 1 is connected to 1, city 1 obviously, and city 1 is connected to city 2 and not connected to city 3. And for city 2 is connected to city 1. Okay. And this is directed so I want to confirm that the city 1, if the city 1 is connected to city 2, the city 2 must be connected to city 1. Okay, I think so. I assume this. Yeah. Okay, so what we want to do is counting the connected component. I see. Okay, I see. So this information is connected. It's kind of a graph. So Yeah, we can use DFS for find the connected component. For example, we start with node 1, and yeah, we can look at the first element of its connected list, and we gonna iterate through this one, and yeah, we have to check one by one, and if it is connected, we can go to the node and to look at the connected cities. Yeah, and yeah, doing it repeatedly. Yeah, that is DFS, depth first search. So so here we want to manage or keep track of which city we already visited. So we are gonna prepare the list for that. And that is like this. Okay. And we call DFS and it starts with 0. Yeah, and this function updates this list. Yeah, mark this list as visited, and yeah, and something like component ID, or yeah, like that. So for the first core, DFS can mark it as 1 because it is like component ID is 1 because they are all connected. So that's a first province, and we are going to iterate through all nodes. We have to call DFS for each node, but yeah, if the node is already visited, we cannot do anything. So that's good. Okay, that's good. Okay, so let's move on to the estimation of complexity. Time complexity is n, where n is already defined, so n is the number of cities. Because we have to visit it every node once, so the time complexity would be n. and the space complexity is this list used for n, and the DFS core yeah, it's n at the most, because we don't call more than n times, so space complexity would be n. Yep. So let's start to code. So we declare the list to keep track of which city is already visited, and this is also used for storing province ID. So let me think about but this function, yeah, we are required to return the total number of provinces ID. Okay. Total number of provinces ID. Okay. Provinces ID. Yep. N is connected, and province ID is 0, and for I in range n, if not visited, I if not visited I equals 0. Oh wait, if visited I equal to 0, it means we haven't visited the city I yet, so we can call DFS province ID to be incremented, and province ID and the node I and the visited no, we already have visited arrays, so we just pass the province ID and the node I think so. And this function, in this function, this list is will be updated and return the province ID, because the province ID at this time after the loop, it represents the total number of provinces, right? Yeah. So let's implement dfs function dfs and province id and node So when call this function, we update visit node is province ID, and then we have information about connections. So connections is we can get from connected at node it's a list of 1 or 0 connections and also we have to exclude the node itself. So enumerate connections, and if I equal to node, it means it's always 1 because it's always 1 so I and we don't need to no we can handle this case in a normal pattern because we already update the visited list. So what we have to do is just check the visited B is yeah, the B equal to 1 and also not visited. So not visited means visited I equal to 0 represents not visited. So we call the DFS next to DFS and its same province ID and the node is I, right? Yeah. This function returns nothing, just update the visited list. So I think this works. Correct. Okay, if there are any edge cases, looks good to me. So let me check. Okay, collect. Union find. But not too bad. Yep. Great. So go to next. Network delay time. You are given a network of n nodes labeled from 1 to n. You are also given times a list of travel times as directed edges times I equal to UI VI WI, where UI is source node, VI is the target node, and WI is the time it takes for signal to travel from source to target. We will send a signal from a given node K. Return the minimum time it takes for all the n nodes to receive the signal. If it is impossible for all the n nodes to receive the signal, return -1. Okay, let me see the example 1. Node, there are 4 nodes and the K is the source node, and what we have to do here is return the minimum time it takes for all the n nodes to receive the signal. Okay, so the node 2 receive the signal, and then it is sent to the node 1 and 3 because it's connected, and it takes time 1, and then the node 4 is remaining, so the 4 and also 4 is connected to node 3, and it takes time 1, so the return the minimum time, so we have to return 2. Okay, I got it. I understand the problem. Okay. Basically, we can receive the start node. So we just process breadth first search. So because we have our information about time, and yeah, when we look at this node, we can get to know the current time is already current time is 1 to reach here, and then we just go to next. Let me see how to construct this graph. We have times. We just have times, and U and V is connected, U is a source node, and V is a target node. So we have to construct the graph, and the challenge here is we have to return the minimum time. So if there are multiple ways to go to the target, we have to calculate the minimum time. Yeah, this is basically Dijkstra algorithm. We can use it. Maybe we can use it. So the concept is like we choose the smaller one. We always choose smaller one, and even if the node is already visited, if we can update the minimum time to reach there, we choose them, and that's the Dijkstra algorithm. So, and the difference is we don't have a specific target. We just n node, and we have to get to know whether all the n nodes are visited or not, right? And even if all the node visited, it's not always the end of the process, because there is possibility to update the minimum time to reach the minimum to reach the node. Yeah. So it seems difficult. But let me think about how to implement. We have to construct the graph is like this, and we start at node 2, and BFS, it uses heap priority queue, in other words, and we always pick the minimum time. So the element is like this. This is node and time. Okay. Node and time. Oh wait, maybe time and node is better. Yeah. And visited, yeah. Visited, this list manages the time to be visited, so it's initialized with the largest value. It represents the node is not visited yet, and for example it's 1000 or something like that, and the node 1, but it starts with node 2, so the initial value is times 0 and 1000 for other elements, right? And when we reach the node 2, we can, we have two options for the next step. The time gonna be 1, okay? So we can append it because the 1 is smaller than 1000, so it's it's needed to chosen, okay? Yeah, if this time is more than current time, we don't need to do it because we cannot we don't have to use it because we want minimum time. So it's a condition to append it to the priority queue, right? So yeah, that's the algorithm. So let's think about the time complexity. In the BFS, we have to check all possibilities in this information because this information means edges. Yeah. So yeah, but we don't do more than these informations. So the time complexity would be O of E, where E is the length of times, means length of edges. Oh, wait. Yeah. We have two parts this process. The first part is to construct a graph, and it also takes O of E because it iterates through the times. to construct the graph, and then we start to BFS, and it also takes the O of E. Yeah. Yes. So the overall E times E is equal to E. So the O of E, and space complexity is we construct the graph, and we also use the visited list is n, and this is also n, I think. No, the one entry contains multiple values. Yeah, it's it corresponding to the number of edges, so overall E plus n, I think. So let's start to code. The time is 100 at the most. So yeah, so it ten thousands in total at the most. So we initialize the visited list. Power of 7, it's enough big, and times n. Okay, and the visited k minus 1. Yeah, because the node label is 1 indexed, so we have to decrement by 1, and k minus 1 is initialized with 0. We can visit the node k minus 1 at the time 0, and we have to prepare the priority queue heap queue. It is Python heap. Python heap, how to initialize. heap push, and heap pop. Heap Q, heap push. I see. Okay, so I don't think I should use. I don't need to. Yeah, I started to think that I don't need to use heap because we have to check the all possibilities, and finally we can find out the minimum time. So I don't need to heap queue because heap is used for choosing the minimum time. Oh, wait. No, it's important. Because when we think about the time to reach node 4, it's based on the time when we reach to node 3, and the time should be the minimum time because it's dependent by the node 4. So if we have multiple options to reach node 3, it must be minimum time. So in order to do that, we have to use the heap queue because it's complicated but basically we have to use this one. I'm thinking about what if we don't use heap queue. It would be wrong or not. Let's assume there are multiple paths to reach node 3. Maybe we don't need to use heap queue. Yeah, because we have to check our possibilities, so we always update the minimum time to reach there. Yeah. That's the difference from the Dijkstra. In Dijkstra, there is a target to visit. So in order to visit the target, we have to always choose the minimum one, and choosing the minimum one and minimum one and minimum one, and after all we can visit the target node, right? Yeah. I think so. So we don't use heap queue, we just use queue deck. Append left, append and pop left. Graph is default linked list. I think I don't use it. Yeah. So time UVW, okay, UVW. So UVW is time 0 time 1 and 2. The graph U append V and W. Okay. V and W, we need it. Yeah, we need target and its time to go there, and we start to BFS. BFS. So here is a base case. We visit the k-1, so I see. I decrement by 1 because it's one indexed. So we change it to 0 indexed. Okay, and we have neighbors. Graph k minus 1. So it's appended to the queue, and here is the normal case. As long as queue there is an element in the queue, we can retrieve the information by popping from the queue its target and time. Right? And we want to update this list. It is target, and we can reach target at time t, right? And the target might have neighbors, so we have to append neighbors to the queue, and the neighbors but what we have to do here is to update the time. So nay 0 and nay 1 plus t, right? And I also care about if already visited. If already visited, we don't need to check its neighbors. So I see. So if t is less than visited target, visited target would be t, and then explore neighbors, right? Yeah. And basically it's initialized with a very large value, and yeah, we can identify if it's visited or not. So if the value if the value is still 10 power of 7, the node is not visited, so we have to return -1. And if they are less than 10 power of 7, we can all visit it, and the visited time is supposed to be minimum time we can achieve. So the final process is like time t is maximum value of visited, and return -1 if t equal to 10 power of 7, and otherwise we'll return t. That's the minimum time. Okay, let me see the result of test. Okay, great. Is there any edge cases? Oh, great. It works. Let me see the first test answer. This is similar to mine. Heap. This solution use heap q, and adjacent matrix. Distance. It's basically same, but I think if I use heap q like this, we can reduce the number of pushing to the queue, because we can check from smaller one, so this condition is likely to not met. Yeah, so the overall time is faster, I think, but basically same. Okay, good. And I have throat ache, but it's still 1 hour, so let me try third problem. Is graph bipartite? Bipartite. Interesting. There is an undirected graph with n nodes. Okay, where each node is numbered between 0 and n-1. You are given a 2D array graph where graph U is an array of nodes that node U is adjacent to. More formally, for each buoy in graph U, there is an undirected edge between node U and buoy. The graph has the following properties. There are no self-edges. Node U does not contain U. There are no parallel edges. Node U does not contain duplicate values. Okay. If V is in graph U, then U is in graph V. The graph is undirected. Yeah. The graph may not connect it, meaning there may be two nodes, U and V, such that there is no path between them. A graph is bipartite. If the nodes can be partitioned into two independent sets, A and B, such that every edge in the graph connects to a node in set A and a node set B. So in this case, we have two sets, 0, 2 and 1, 3, and the edges every edge in the graph connects a node in set A and a node in set B. So every edge is connected to both of set. In this case, this edges is connected to the node in the same set, so that's false. There is no way to partition the nodes into two dependent sets such that every edge is connected to node in one. So if I want to this edge is, and if I want to make this edge valid, 0 and 2 must belong to the different set, and if I do so, the A and B, what is this, A or B? If A, A, so not good. If B, B, so not good. So we cannot make it this. How do I solve this? Maybe there is a triangle. I think there must be same nodes in the same set are connected, so that must be false. And square is good, but how about the pentagon? Pentagon, there are five nodes and five edges. 1, 2, 3, 4, 5, and there must be adjacent nodes in the same set, because the number of nodes are the odd number, so yeah, so that must be false, I think. So what we're gonna do is to find cycle and count the nodes that consists the cycle. I think so. I think so. A node is 100 at most. So yeah, I think this is the key idea to solve this problem. Yeah. Time complexity is, we have to visit the all nodes. Oh, wait. How to find in this case, how to find the triangle or square? Okay, we have to keep track of paths. So the time complexity is O of E, not N, because we have to explore all edges, so time complexity O of E is the number of edges. Space complexity um of N or E. The core stack, the number of core stacks, the length of core stacks might be E. And the paths, we have to keep track of paths for each DFS, so it might be N because there is node N. Okay, let's get started. So find cycle. It takes and node and pass 0 1 2 3 0 0 1 2 0. We have two paths, so zero, 1, 2, and we call 0. So it means this is the base case. Past 0 means the node to start, and it might be same as a node. Okay. So return true because we find the cycle and we have to return the number of nodes that consist that cycle, so it's length of path 0 1 2 and the node is 0. It's 3. Okay. Yeah, and otherwise return false. It cannot find the cycle. It's good thing. Oh wait, I have to think about that. There are no cycle. Yeah, if there are no cycle, that is a kind of tree. It should be colored by two colors, so it's no problem. So yeah, we just focus on the cycle, finding cycle. So the basic idea is graph. I need I need n you given to 2D graph. UMV. Yes. So, and this is good. I can get n. That is number of nodes. So we have to for I in range n and find cycle. Node is I and path is empty. And the num is that's odd. Yeah. Return false. Otherwise we check all of oh wait visited is needed. Visited. If we introduce visited, zero, 1, 2, 1, 3. But visited is needed, necessary. Need to introduce visited, but yeah. How about this case? Return false. I'm not sure here. we append the path and graph node. We can get neighbors and maybe this function returns multiple possibilities. That means wind cycle. Okay. Cycles. So just return. Cycles append lem path. Okay. And return it. If there is odd cycle, return false. I see. Is this correct? I'm not sure. Path is I'm not sure. Maybe this doesn't work in some cases, but I want to see the test cases. Okay, let me use this case 3. Mm. Hmm? Two is 1 and 3. One is 2 and 3. 0 is 3. Okay, so there is a triangle. There is a triangle and we cannot find the cycle. Oh, this is not good. So Mm, index. But it might be value error. That's not cool. So starting point, if start equal to node, there is a cycle. So if there is a cycle, even if we find the cycle, we don't need to return it immediately. We can continue to search. We can continue to explore. Yeah. And when we find the cycle, we want to append the size of the cycle. How to do that? We have I, and so zeros. Minus I. Correct. We can find 3 and 3. 3 and 3. It must be 3. But it's okay. Let me it's not good because time complexity would be E, its number of edges. 1, 2, 3, 4. 1, 2, 3, 4, right? But 1, 2, 3, 4. I think it's good. Because we want to find the cycle, so before we check the visited or not, we have to process this. Because to find the cycle, the node should be already visited, so we cannot we have to find the cycle before checking if the node is already visited or not. Yeah, and after that it's visited at once, so it's, I think this is good. Wrong answer. What is it? Three and 4. What expected is true. Okay. Zero is 3. 0, 3. 0, 3, 1, 2, 4, 2, 1, and 0, 1, 2, 3, 3, 0, 4. There is no cycle, I think. There is no cycle. There is no cycle. Yeah. There is no cycle and 0, 3, 4, 1, 2. What the what? I see the problem. This is a little bit complicated because we have to exclude the node already visited. So when we reach to here, we've finished exploring, but this process is executed and path is greater than 2. Yeah, because it contains all of nodes, and we loop it. And what? 2 is connected. Just 1. What happened? What happened? Four and 3. What happened? 4 and 3. 4 and 3. Maybe we have to backtrack. Hmm? Three. let's think about this case. 3 and 4 is appended, but this is, the node is 2. Oh, okay. Huh? Why? Zero, 2, 3, 3, 2, 0, 3, 2, 4, 4, 2, 1, 1, 2, 2, and 2, 2, 1. Four, two, one. 4, 2, 1, 1, 2, 2. Why? One, two, 2, 1. 2 is connected to 1. Okay. The 1 is connected to 4. I see. So, So when we have trees, this might be going back, and basically it should be validated by this condition, but this process happens before this, so yeah, so it's not good. So it is filtered by this condition. Let's go. Wrong answer. Let me see the cycles. 447436 false, but the true. 0 4 and 6 4 6 and 0 1 2. Oh wait, one, two, three. One, two. Six, 0 1 2 3 4 5 6. 6 is also 0 1 2 3 4 4 5 0 1 2 3 4 7 8. 7 8. 0 1 2 3 4 5 6 7 8 9. 9 is isolated and expected true because one, two, three, four. 1 2 3 4. 1 2「 1, 2, 3, 4, 5, 6. Yeah, I think so. This is true. Cycle. There are 3 cycles. 1, 2, 3, and for each size is 4, 4, 6. Yeah. So we expect 4, 4, 6, but there is 3 and 7. That's not good. Ouch. Let me see, the size is 7 and 3. This one. Zero, 3, 1, 6, 2, 7, 4. 6, 2, 7, 4. 6, 2, 7, 4. 2 and 7 is not connected. Wow, what happened here? Maybe tracking path is wrong, I think. Node neighbor. What happened here? 2, 7. 2, 7. 2, 7. 2, 7. Yeah, the path is not good. I think we have to copy the new path here. Oh, great. Let me see. Not bad. But there is a fastest answer. It's DFS and color 0, and if there is no color, no color, or we call next DFS. Otherwise, else if the color is the same as neighbors, return false. Oh, this is cool. This is cool. So the C might be 1 or 0, because if it's 0, the neighbors would be 1, and when we call this function, the neighbor's color would be 1 and its neighbors would be 0. So the colors are initialized with -1, and when it is visited, it should be 0 or 1. And if it's already visited and it's same color, that's not good, so we can return false at the time. And when we explore all the colors, all the nodes where we can explore, we return false because it's valid. We can color 2 areas. And we explore all nodes, but as long as it's not visited. Yes, I see. Cool. My implementation is not efficient because at here we loop. We iterate through the path, so this is not correct. Okay. But in this problem, the n is not too large, so there is not too slow. It's not too slow. But I think this is an expected answer, and it's a smartest solution. Okay. Coloring problems. Okay. I solved 3 problems today, and yeah, I'm getting better at graph problems. See you next time.